Dear students, I have the privilege to stand before you to share some lessons which we couldn't complete during the normal classes because of this pandemic epidemic. We need to acknowledge the college management to organize such lecture series during this social distance period. I pick up one important lesson in the syllabus under Dhanmanjuri University, Impal. The topic is quadrature to find the areas of plane curves. You know, you have studied mensuration to find the areas of different figures in lower classes, but this quadrature and areas of plane curves are quite different. And as we have earlier done about the reduction formulae and all, then we apply this definite integration to find the areas of plane curves. So the mode of the talk will be like what is quadrature, second is intervals, then third is a techniques of calculation, number 4 is take the limits of applying that definite integrals. When somebody asks you about the definition of quadrature, you can answer like this, that it is the process of constructing and determining areas of regions bounded by curves, as I have given the definition. So intervals, for the intervals you know the specific endpoints of a region in the continuous function. And in the techniques of calculation, we need to, number 1, define the equation of the given curve. Then second one is integrate the given equation by detecting the intervals. And then after that, after integrating and put the limits, then you will find the area of the given plane curve. The main point is to find the area under a curve. The area under a curve between 2 points can be found by operating a definite integral between 2 points. Number 2 is to find the area under the curve. Say suppose y is equal to fx, as I give here, between the intervals x is equal to a and the x lower limit is x is equal to b. We integrate y is equal to fx between the limits of a and b. So one example we can cite to find the area of a quadrant of the ellipse. Standard ellipse is, as I have given the equation here, x squared by a squared plus y squared by b squared is equal to 1 between the major and the minor axis, as the figure indicates. You see, the major axis is represented by the x-axis and the minor axis is represented by the y-axis. But the alternate of the method also can be applied in your case. It is clear from the figure that the area to be calculated is bounded by the curve, the x-axis and the ordinates x equal to 0 up to x equal to a. Then the required area of the quadrant that is represented by d is given by d is equal to integration from 0 to a y of dx. We need to integrate. So as I have given the standard equation of the ellipse as a y square x squared by a squared plus y squared by b squared is equal to 1. From there you can transform y in terms of x as y squared by b squared is equal to 1 minus x squared by a squared. So this transforms that y squared is equal to, say, b squared by a squared into a squared minus x squared. Therefore y is equal to b by a under square root of a squared minus x squared. Then y can be, say, interpreted as integration from 0 to a b by a under square root of a squared minus x squared dx. Then this is again equivalent as integration from 0 to a b by a under square root of a squared minus x squared dx. So now here we put, say, x as a sine theta. So that, why? Because dx is equal to a cos theta d theta. Therefore this result can be put in the previous integration, that this is equal to integration b by a integration from 0 to pi by 2, because the limit has been changed from a to pi by 2. Then a cos theta into a cos theta d theta is there already. Then this is equal to b by a integration from 0 to pi by 2 a cos theta into a cos theta d theta. This becomes b by a, and then you can bring out a square outside of the integration, and the integration from 0 to pi by 2 cos square theta d theta. Then this becomes ab integration from 0 to pi by 2, and the cos square theta is nothing but 1 plus cos twice theta by 2 d theta. Then this is equal to ab by 2 integration of from 0 to pi by 2 1 plus cos of twice theta d theta. From here if you integrate, then this becomes ab by 2 then theta plus sine twice theta by 2. The integration of cos twice theta is nothing but sine twice theta by 2, and the limit is taken from 0 to pi by 2. In this case this becomes ab by 2, and the value of sine twice theta by 2 will be naturally 0 in both cases. That means in the case of 0 also, in the case of pi by 2 also, because sine 0 degree is always 0. Therefore the value is taken here in the case of theta. Theta becomes pi by 2. Therefore this becomes ab by 2 into pi by 2. This becomes again pi ab divided by 4. Remarks: this is the area of a quadrant in the standard elliptical form. So one remark is there. Number one is that then the whole area of the ellipse is clearly 4 times the above result. That is that means area of the ellipse is equal to 4 times of pi ab divided by 4. 4 cancel out, then you will get the area of the whole ellipse is equal to pi ab. Second one is, this is very important, putting a equal to b, that means major axis is equal to minor axis, and proceeding exactly as before, the equation will become x square plus a square is equal to a square, which is the equation of a circle. Here the radius will become automatically a. Area of a quadrant becomes 1 by 4 pi a square. That is, the area of the circle is pi a square, as you know. It is absurd that the equation of an ellipse will become a circle when the major axis equals to the minor axis, as I have shown in the figure. So taking this relationship, we can do another example, that is parabola. In the case of parabola, as you all have known, determine the area of a parabola y square is equal to 4ax bounded by this parabola and any double ordinate of it, say x is equal to x1. Here the area, as you see in the figure, OAB is bounded by the curve y square is equal to 4ax, the x-axis, and the 2 ordinates, say x is equal to from 0 to x1. Hence the area of the figure OAB region, OAB is given by area of OAB integration from 0 to x1 y dx. Say from here, from the equation of the standard equation of a parabola, you can convert y in terms of x as we have done in the solution. So this is equal to from integration from 0 to x1, y is represented by under square root of 4ax dx. We take here in this case only the positive values of y. So now this becomes integration from 0 to x1 under square root of 4ax dx. Then this is equal to under square root of 4a whole 2 by 3. The integration of x power half is nothing but x to the power 1 by 2 plus 1. This becomes 2 by 3 x1 y1. Why? Because we have taken the value as y1 is equal to under square root of for AX1. Therefore, the required area of AOB is equal to 2 into 2 by 3 x1 y1. This becomes 4 by 3 x1 y1. So one remark is here, the area of region bounded by the parabola and its lattice rectum is always equal to 8 by 3 a square. So taking the above techniques, you can find out any area of a given region of plane curves, for example conicoids, provided the intervals are given. So with this I wind up here for this day, and if you have any queries and doubts, then you can go inside to the link. Thank you.